All right, how's everything going? So ODP 214 okay? I think that's it for ODPs for the week. But we will get back to more of them later. So let me just run through some code from PA2 just to sort of see one implementation of PA2. This really mimics the PA1 code that I showed you after PA1 was turned in. The struct node is, what we've been working with, a data field and a next field, which is a pointer to a struct node instead of an index and an array. The function prototypes are all the same, except init returns a struct node star. Usage tells the person how to, what the legal commands are. Process parses the input line, does whatever it's supposed to do. The main program is the same, except list is a struct node star instead of an explicitly declared array of struct nodes. And list gets its value from init. Okay, so init creates a sentinel node, and we take the return value from that, and that's what list is. So init returns the address of a sentinel node created somewhere in memory. The main loop is exactly the same, and I check for end of file with a control D. Process should be exactly the same, right? This is just parsing the input command field, which is in this variable buffer, and deciding if you're trying to do an insert or a delete or a print or whatever. And so none of that changes, except that at the exit case, I call this function release to free all the memory. Help message doesn't change. So init is simpler than it was in PA1. We just make a single call to malloc, and we set the next field of that node to be null, and we return that node's address. And we don't have to go through and set valid bits to 1 because the operating system is managing that for us. That's all heap management. The area of memory that malloc pulls from, that's all being taken care of for us. So add, almost exactly the same code. Alright, so here's PA2's add. So node is initialized to be the sentinel node, is previous, and current is the thing that the sentinel node points to. Okay. In PA1, previous was 0, that's the index of the sentinel node. Current was list bracket 0.next, that's the index of the first data node, right? Or possibly null or my null. So we create a new node by calling malloc. Okay, in PA1 we created a new node by calling get node, right? And we checked to see if it returned null, and if it did, we were out of memory. So in here we call malloc, and if malloc returned null, we're out of memory. Otherwise, set the data field to our number, and now our new node is mostly set for insertion. So one thing that I saw a few times in PA2 is the following, something like this. All right, so first there was a statement which said, if malloc returns null, then we're out of memory, return a 0 from, this will say, our add function, right? So if malloc returns null, return a 0. Otherwise, call malloc to get a sentinel node, right, set sentinel equal to that. Okay. This is a guaranteed memory leak, right? Because as soon as you call malloc, yeah, you're just calling it to see if you're out of memory, but that's allocating a chunk of memory.
But what it should be assign a pointer to the value of malloc and then see if the pointer is equal to 0?
Exactly, right? So when you call malloc, we don't know if we have memory or not, but let's save the location that it gives us and check to see if that's null. If that is null, we know that we're out of memory. Otherwise, that thing that we got back from malloc, that's our sentinel node. Yeah?
How did you test this?
How do you test what?
Or did you test that?
Oh, how did I test PA2?
Yeah, that part.
Oh, that part I would only find by looking in the code, but this will definitely leak memory, right? Because once you do this malloc, if I don't save that address that I got back, I got no way to free it. Okay, so this will at least show up in a Valgrind memory leak. So yeah, I don't have to actually find it. Yeah.
No, I was just going to say, find it without
Yeah. The other problem is that sometimes, right, you do this to see if you're out of memory. Suppose it says no, you do have memory left. What's possible, you just allocated the last piece of memory that's available. And now when you do this, you might still get null here, right? Every time you call malloc, you get a different value. You could run out of memory at this point. And if you're assuming that sent is not null at this point, that can cause problems later on. So there's a few things to watch out for here. So do it like this. All right, so that's just a detail. Okay, so we're adding, so we have to use a pair of pointers, current and previous, right? We set up previous to be the sentinel, we set up current to be the node after the sentinel, and this parallels what we did in PA1. And we loop through until the current node is null, and at each point we check to see if the current node's data is bigger than our num, and if it is, then we want to insert our new node between previous and current. Same thing happening here, just different syntax. So while current is not equal to null, right, check the current node's data. If it's bigger than num, we want to insert between previous and current. So previous, we change it to point to the new node, and new we change to point to the current node. That squeezes it in between the two, and then we're done. Otherwise, move down the list. Have previous point to the current node, have current point to the node after current. And if current was the last node in the list, when we make this assignment right here, current equals current next, current will be equal to null, which will kick us out of our while loop. So if current was the last node and that was not what we wanted to insert before, we come out here, we know we want to add to the end of the list. So have, so at this point, previous is the old value of current, have that point to our new node, have our new node point to null. And that's the same thing we did here. All right, this moves down the list in PA1, and this inserts at the end of the list, right after previous. So it's very much a parallel structure. But this previous next equals new should eventually tell you, oh, previous is pointing to new. Whereas this list bracket previous dot next equals new is a little bit less obvious what's going on there. All right, the print function is exactly the same, other than the syntax of list arrow next instead of list bracket next dot, or list bracket dot next. Delete is exactly the same thing, para nodes previous current. Do what you have to do to squeeze out the node in the middle. Search is the same. So release is a different function, because we need to free our memory. So let's make a list. So let's see, our list has 3 nodes in it. So we call our release function with list. So this is the node that list refers to. And we start off by saying PTR equals list. So pointer is a temporary pointer. Free this is another temporary pointer. So we seed PTR to be the first node, the sentinel node. And then while that is not null, well, that's actually referring to a node, we do the following. Free this equals pointer. So we say free this. And that's just going to remind us of the node we're about to free. And then we say pointer equals pointer next. So we change pointer to be the next node. And now we don't need to know this node's next field anymore. We've saved it so we can free that node called free this. So that's the bottom of the loop. Free this. That releases this from memory. Go back to the top. Pointer is not null. Set free this equal to pointer and set pointer equal to pointer next. Now we're completely done with this block of memory, so we free it. Go back to the top of the loop one more time. Pointer is still not null, so set free this equal to pointer. Set pointer equal to pointer next, which is null, so now pointer is null. We'll still call free this. And now we come to the top of the loop. While pointer is not null, pointer is null. And so we're done. We know we freed the whole list. We just return at that point. So that's that freeing one step behind your business. So any lingering questions on PA2 or linked lists? Yeah.
I mean, this question is more related to PA3 though.
Mm-hmm, that's fine.
So, what is it? So when I was trying to test out one of my, it was like my list add function. I was trying to print out, I was just doing a bunch of print statements to see if like was actually adding to the list.
Okay.
But I guess I don't fully understand the arguments for printf. So when we say %s, does that include a car star?
%s will print a car star
Okay.
as long as that car star points to a valid location in memory
Okay.
and contains hopefully a bunch of printable characters followed by a null terminator. Right? The compiler will be happy with a car star, but it should be pointing to an actual set of characters.
Okay. Currently I'm getting null for my print statements.
Okay.
I don't know why.
Probably because your car star is pointing to null. Is this like for a plate or a first name or something?
For all three.
Okay. And you've stored stuff in there?
Yeah, so I checked for GDB and
Mhm.
gave, when I was saying like print, plate, first name, etc. It showed that the plate name that I wanted to give it, the first name I wanted to give it, last name, etc. But I guess once it goes through the printf statement, it doesn't.
If you can see it in GDB, printf should give you the same thing you're seeing. But
So-
there's some wiggle room in that.
Okay.
Can you show me a 12?
Unfortunately, that's 12.
Okay.
I could send a screenshot of it.
Yeah, the more information you include, the better. Most screenshots I get don't have nearly enough information.
Okay.
But you can try it. Doesn't hurt. But yeah, otherwise come by the office sometime and we can look at it. Yeah.
Would it depend on what the variable you're sending to us is?
But you're sending plate or first name or last name, right?
Yeah, same plate. First name, last name.
Okay. What are you doing in GDB to look at it? Are you saying print plate?
I'm saying print and then the node and then its field. So node, arrow, plate, node, arrow, first, arrow.
Mm-hmm. Yeah, we gotta look at it.
Okay.
Yeah, usually the problem is particularly with PA3, right? These car star fields need to be given space
Okay.
somewhere. Are you calling malloc and assigning it equal to the result of malloc?
What do you mean by that?
So if you have car star plate, right? And are you copying into plate with an equals or with a string copy? Okay, so there's two issues, right? One is if you want to copy the contents of an array of a string into plate, you really want to use string copy. Right, or if you're using quoted strings or something like that. And before you can do that, you have to set up some space to copy those things into. If instead you just do plate equals something, right, whatever that something is, if that something changes down the road, plate will automatically change at the same time. So if this is a temporary variable and you change the value of that temporary variable, even though you said plate equals that, plate will change. Because this isn't copying characters, this is saying plate refers to the same thing that this refers to.
Interesting.
Yeah. That's one of the weird things about strings in C.
I can tell that I missed the string copy stuff.
Okay. And string copy will segfault unless you do a malloc first.
Okay.
So, yeah. Yeah, strings in C, remember, right, so I've got a car star copy, I've got a car star original, which I'm setting equal to hello. I set copy equal to original. If I print copy, it will print hello. Okay, but now if I say something like, you know, original bracket 0 equals null terminator, to change original from hello to just an empty string, and now if I print copy, I'll print an empty string. Right? The reason is that ORIG is an address in memory. It's the address where this string is stored. Now I'm taking what's at that address and I'm putting a null terminator there. Copies the same address.
Yeah, it's the same address and address.
Yeah, yeah. This actually will give you runtime errors because you can't change a quoted string, but ignore that. All right, other questions? So it turns out there's other things we can do with lists. One nice variation is a doubly linked list. And with a doubly linked list, our nodes look like this. There's a piece of data. There's the next value, which points to the next node. But there's a third field, which we can call previous, which points to the previous node in the list. And so our list might look like this. Here's a 10. Here's a 20. Here's a 40. And the next fields point through like that. But then we have these previous fields which point backwards. So this previous points back there, this previous points back there, this previous points to the node before it, and some other node after the 40 is pointing back to the 40. Oh yeah, our nodes are bigger, we have an extra address in there, but this really simplifies our logic, because this business of having a previous and a current, or a current and a next, this pair of pointers, we don't need that anymore. For example, suppose you want to delete a node. Suppose you want to delete the 20. we do a very straightforward loop, just like when we're printing. Start off with a node after the sentinel if we have a sentinel. If that's equal to 20, we're going to delete it. Otherwise, set node equal to node next. Let's say that our temporary node is right here. We don't need to remember what the node was before it. We can get to it through the previous field. So if we want to delete temp, we've got all the information we need in that one node at temp. So what do we have to do to delete temp? We need to take the prior node, the previous node, and have that point where temp is pointing. Okay, how do we get to the previous node? Temp arrow previous. That's this. And we want to set that to whatever temp is pointing to. So temp arrow previous equals temp arrow next. Not quite. This node is temp arrow previous. We want that thing's next field to be whatever temp is pointing to. So temp arrow previous, arrow next equals temp next. Alright, temp previous next. That's this block right here. Set that equal to this address. That sets up the forward pointer to skip over the 20. And then we need, yeah.
Can you give a little bit of real life example?
More real life than this.
Just conceptualizing better.
Let's see. You mean a code example or like a practical application or? Oh, any of the stuff we've been doing with lists, right? The issue is when we want to delete, we can't just say, here's the node I want to delete. We got to know the node before it, so we can say, have that previous node point to the one after, right? If we're doubly linked, basically we can just use temp previous to get to the node before it. So we could do something like this. So let me draw our picture of a struct node. Here's data, here's next, here's previous. And let's say this is a 10, and a 20, and a 40. Alright, so the forward pointers go like this, and the back pointers go like this. Okay, here's all we're doing really. Let's say this is temp. Let's say this is current. Okay. All I'm really doing is saying, you know, prior equals current previous. So this is prior. And the following node is current next. So this is following. Well, if I have a name for this node and a name for this node and a name for this node, deleting the 20 is pretty straightforward. To delete the 20, so delete the current node, all I've got to do is set prior so that it points to following. Right, set this up to point to the 40. And to set the back pointer, I just need following previous to be equal to prior. So this back pointer, instead of coming to the 20, will come back to prior. And now my picture looks like this. So I've changed prior next to be the 40. I've changed 40 previous to be the 10. And I've still got, 20 pointing out here, and I've got 20 pointing back to here. But I'm going to get rid of this block anyway. I'm going to say free current, and this is going to go away. But as far as my linked list, when I get to the 10, the next node is the 40. If I'm coming back and I get to the 40, the prior node is the 10. Right, so I can set up temporary variables for the node before and after current, and then just adjust their pointers. Does that make more sense?
A little bit, but how do we decide which one is single or double?
So doubly linked is a little more memory, right? But if you don't feel like dealing with keeping a pair of pointers, right, doubly can be nice. Because you can go backwards. Sometimes we may want to find, suppose you want to find the third node before some particular value, right? To do that practically, you'd need to sort of keep track of a temporary node, right, which is 3 spots back, and update that as you move. And so on here, you could just find the node you want, go back 3 hops. And some of the algorithms we deal with, not with lists, but with trees, which are a form of lists, will actually need to do things like go back 2 nodes and then come forward another node, and things like that. It's generally easier to deal with these, other than the fact that you've got to update a pair of pointers now. But once you're used to it, right, instead of saying prior arrow next equals following, where prior is current previous, we can just write this as current previous. That's prior arrow next. Equals, and instead of setting it equal to following, which is current next, we can just say current next. A lot going on in that statement. But once we understand that, what does it mean? Take the current node, go back to the previous, see where that's pointing, right? Set that equal to what my current node is pointing to. That sets up this link from 10 to 40. Okay, so let's do a practice. Let's insert. Let's make a new node with a 30. And we want to insert this into the list. So we have forward pointers. And we have back pointers. And we want to insert a 30 into this list. Now we're going to do the same thing we did usually, but we're not going to keep a pair of pointers. We're just going to walk through and find the first node whose data value is bigger than 30. Okay, and I'm going to call this temp. So while temp is not null, if temp data is bigger than new data, then insert new right before temp. So we want to squeeze this in right before temp. And all we need to know is what temp is and what new is. All right, so here's our picture of our nodes. Data, next, previous. All right, somebody give me a line of code that I could use to help insert this 30 right before the 40. Insert new before temp. I've already done some stuff, and now temp is pointing to this node. New is my new node. We're going to have to do 4 things, so somebody give me one thing we have to do to adjust the pointers to put this in between the 20 and the 40.
Arrow previous is equals to
Start again?
temp arrow previous.
Okay. Temp arrow previous equals new. So we're going to change this to point back to new. Cool. So there's a back pointer. So now if we look at temp, which is node 40, and we say what comes before it, it's going to be node 30. Perfect. There's one. All right. Anybody else? Another line of code.
So I think before that, you have to say, new arrow previous is equal to temp previous.
Let's see. New arrow previous equals temp arrow previous. So news previous is going to be whatever temp is pointing back to, right? So yeah, we want to do that before we change temp arrow previous. So temp arrow previous is pointing to the 20. This will say new previous should point to the 20. That's going to go back there. Awesome. All right, so we have our back pointers set up, right? Something is still pointing to 40. 40 points to 30. 30 points to 20. 20 will still point to 10 because we're not changing that. Back pointers are square. What about the forward pointers? Go for it. New next is equal to temp. So news forward pointer should go right here. Looks perfect.
New arrow previous arrow next.
New arrow previous, arrow next equals new. New arrow previous is now pointing to the 20. Set the next field, have it set equal to new. That sets this up to point there. There's your forward pointer. So 10 goes to 20, 20 goes to 30, 30 goes to 40. The forward pointers are set up. Excellent. So we got to do 4 things. But we didn't need to keep track of multiple nodes. All we needed to know is what's the node we want to insert before. And we can find the prior node by saying, you know, prior equals temp arrow previous. And if we have a sentinel node, we don't have to worry about nulls, right? Because worst case, previous would be the sentinel.
Doesn't this considerably reduce our operations?
Yeah.
Because inevitably you have to include that you're always sending the previous variable to something.
Yeah, so as you're walking through, you got to keep track of the previous. That's more operations to perform. If your list is very long, that could be significant. Once we get to the spot, then it's always just these 4 operations. So doubly linked lists are nice to have sometimes. The other thing I'll mention is a circular list. And a circular list, basically, when you get to the end, instead of that last node pointing to null, points back to the first node. And if you have a sentinel, it probably points back to the first data node. And this can be nice because if you want to just keep circulating through the stuff in your list, you don't need to see if the node is null, and if it is, go back to the thing the sentinel points to. You just keep following the chain of next. Go to next, go to next, go to next. You can do that 1,000,000 times, and you'll just keep running through the different nodes in your list. Bless you. That can be convenient sometimes. I don't know, say you're bowling, you know, and you got 4 people sharing a lane, and you want to know whose turn it is, and so you implement a linked list and code it up on the little machines they have in bowling alleys. And after the fourth person bowls and you say, tell me who goes next, it'll just go back to the first one and say, oh yeah, person so-and-so, right? It's an everyday application, not really. And you can make a circular doubly linked list. Same thing, you have back pointers and the first node points to the last node. And we'll see some applications of these. It's a little tricky to print a circular list though, because if you just keep following the next node and print until you get to null, you never get out of your print loop. And this happens in some PA1s and PA2s, right? We sometimes inadvertently create circular lists. We'll do this a lot when we're dealing with trees. We'll accidentally have something that instead of pointing to null points to another node, and we can end up chasing our tail. So if you're playing with this stuff and you start spewing output, right, you've probably got something circular somewhere. But you know, if you're trying to print this, you simply note the address of the first node, and then instead of seeing if the next node is null, see if the next node is the same as the address you started at. And if it is, now you know you're about to repeat yourself, and you can exit at that point. All right, any other questions on that? Yeah. The circular? Oh, yeah. So new previous is going to be 20. Yeah, because we said new previous equal to temp previous. And so we set 20's next to be equal to new. Alright, so this is the 20 node. And then we set 20's next to be equal to new. New previous is 20 because the first thing we did was we said new previous is equal to temp previous. So we made new point back to whatever temp, which is our 40, was pointing back to, which was 20. So this was temp previous. So we set new previous to be the same. So new previous went back to the 20. And you can use temporary variables as another way to look at this. I could set prior equal to temp previous, and then this would be prior arrow next equals new. And new previous equals prior, and so on and so forth. Does that make more sense? Okay. All right, so let's talk about stacks. So a stack is another, oh yeah, go ahead.
Before you get into that, are you going to talk about the
Lists.
Are there any questions on GDB in there?
5 programming questions, that's it. 5 snippets of code or functions that you will write. One of them will be just snippets of code related to structures. So working with structures, mallocating space for structures, addressing the fields of structures, things like that. And then 4 of them will be functions related to linked lists. Functions you have not written yet as part of an assignment, but doing the same kinds of things that you've done in the functions you have written related to linked lists.
So not double lists?
I won't ask you doubly linked lists or circular lists. And I won't ask you how to spell hexaflexagon or or what the GDB such and such command does or things like that. It's purely programming. Final will probably have some short answer, multiple choice questions like that, but midterm I really want to see where people are with linked list code. So best way to study, right, go through your code, try writing code, try making a doubly linked list and inserting into it, right? It's not going to be on the exam, but it really gets you some good practice with dealing with these arrows and sort of relating pictures to code and so on. You know, you never want to try to memorize these 4 instructions, right? What you want to be able to do is draw a picture that makes sense to you, figure out how you want that picture to be changed, do whatever you're trying to do, insert, delete, search, and so on, and then, you know, write down code that corresponds to each of those changes you make. Well, I want this arrow to go here instead of there, right? So how do I access where that arrow points, and how do I access what I want it to point to, and let's set those equal, right? Or you can write code, maybe that you've already written, and you can take pictures and you can say, what does this instruction do? Update the arrows. What does this instruction do? Update the picture. And see if when you're done, the picture is updated in the way you want, right? So for me, I start with pictures. I think about how I want this picture to be manipulated. I write code to do that. And then if I'm debugging, here's what my code is supposed to do. I'll update a clean picture and say, this is what I'm telling my memory to do. Is this correct? Right? And maybe you'll find, oh, I'm pointing back to myself instead of the next node. So being able to make those connections, right? That's to me the key to working with these data structures, whether it's lists or stacks or trees or anything else. And so that's probably really good practice for the midterm. Is, you know, rewrite your linked list code. Or do something different with your linked list code. Write a function that deletes the second element in a linked list. Right? Something that always deletes the second node of a linked list. That's not particularly useful to us, and it's not something we've ever done in this class, but being able to do that is really good practice, right? Getting to the point where you're able to do that is really good preparation. Just because it gets you thinking about what am I actually doing, because sometimes we get so entrenched in, you know, this is my add function, this is my add function, this is my add function. We kind of forget, like, what the bigger picture is of the add function. Now if we have to do a variation on an add function, it's like, you know, it's nothing to do with anything.
So is that kind of like close to what we've been doing daily feeds?
Yeah, yeah. So sort of on that level. Cool. All right, so let's talk about stacks. So suppose I'm standing up here and I'm about to introduce stacks to the class. So I'm planning to start talking about stacks, and I get a piece of paper and I write the word stacks on top, and I'm about to launch into something about Chinese restaurants as part of my explanation of stacks. And a question comes in which says, what about the midterm? Okay. So do I abandon the idea of talking about stacks forever and say, well, we'll talk about the midterm and then I'll talk about something random, right? No. So I tuck this away somewhere in my memory and I talk about the midterm. And maybe while talking about the midterm, someone asks, what about pages of notes? What are the limitations on that? And I don't remember, so I tuck this away and I pull up Canvas and I see what it says about how many pages of notes you're allowed. Okay. When I'm done with that, and I've said, okay, so it's 4 pages double-sided, I'm done with that. Do I jump back to talking about stacks? No, I jump back to where we were talking about the midterm. How many questions are there going to be? That kind of stuff. When we're done talking about the midterm, I get rid of that. Now I jump back to talking about stacks. Okay, this is a stack-based process. The idea of the stack is when I'm doing something, if I start to do something else, when I'm finished, I'm going to go back to what I was most recently doing. So I'm doing task A, task B, task C, task D. When I'm done with D, I'm going to go back to C. When I'm done with C, I'm going to go back to where I was in task B when I got interrupted. And that wasn't an interruption. And if I'm working on B again and something else comes along, task E, I'll pause what I'm doing in B and I'll do E. And while I'm doing E, I'll go off and do F. And when I finish F, I'll go back to E. And when I finish E, I'll go back to B. And when I finish B, I finally get back to task A. And if I finish task A, then my stack is empty. There's nothing I have to do. So we deal with stacks in real life, right? We use them all the time to sort of keep track of where we are when we're being distracted by something else that we're going to shift our attention to. We do this when we browse the web. You're looking up, something on Canvas, and all of a sudden you hear a siren outside, and so you go to the local news page to see what's going on, and there's something about a garage sale this weekend, so you click on that to see where the garage sale is, and it's so and so, and you're like, oh yeah, that reminds me of something else, and you go and you look at that, and you're building this long chain of like things that you were doing, and you got interrupted and started doing something else. When you're done with that last distraction, you hit your back button, and it brings you back to where you were on the previous page. And you might read that page and get distracted and follow some other links and then come back to that page. And eventually, you probably come back to the first page where you were looking up, something about the assignment on Canvas. And if you were in the process of making dinner, when you suddenly realized you needed to find this thing on Canvas, when you finish with Canvas, you go back to making dinner. And right, so we sort of work with a stack-based model. So computers do the same thing. Computers, a lot of the processes they do can be interrupted, and when they're interrupted, you go off and do something else, and when you're done doing that something else, you come back to where you were. So how many people have done Engineering 270 already? Right, so when we have interrupts in there, and we talk about the stack in there, it's the same thing. Okay, if you get interrupted, you save where you are on the stack, you go off, you do something else. When you say retfee, you come back to where you were as if nothing had happened.
Can it multitask though?
In what way?
So it does A and B.
That's another question. So on a PIC processor, no. On a single core CPU, no. On a multi-core system, sure. But that's a further complication. We will get into that in 223 though.
Okay.
We'll actually deal with multitasking. All right, so we'll look at this in a more concrete sense with numbers going on a stack, and then we'll talk about stacks as an abstract data type, and then we'll start looking at implementing stacks. And we can implement stacks with arrays. We can also implement them with linked lists. Okay, so we'll look at both of those, and then eventually we'll move into another data structure called a queue, which is an analog to a stack but different. All right, so I will see you next time.